Hi, Doug Van Eaton here. Welcome to what for many of you may be your first bit of video instruction if you had the good sense to skip ethics and leave it to the end of the study season. You're starting off in study session 2 here with our first reading, the time value of money. So these are very important concepts. You need all this stuff. You need to get it down. You'll use it all through level 1. You'll use it all through level 2. You'll use it all through level 3. So with that in mind, let's jump into it, get some of our basic concepts and definitions down, and then look at some calculation techniques. Now, we talk about the interest rate, and we say that money has time value. What we mean is that more money later has to be equivalent to less money now, because people prefer to have money now than later. And we know that because interest rates are positive. So your choice is, if you have $100 today, if the interest rate's 5% a year, you could have $105 a year from now. Now, inflation may come into it, prices may go up, and we'll take a look at this too when we talk about real interest rates. But with positive interest rates, money now is preferred to money later. And so we've got to have a way to talk about, well, if I invest this much money now and I get this much later, is that a good deal or not? Is that something I want to do or not? Now, we usually look at interest rates through what I'd call a build-up method here. And we've got 3 definitions. First one is it's the required rate of return. So in equilibrium, when we say the required rate of return on an investment, we mean that investment is priced so that its expected rate of return is in equilibrium, and we say, well, that's the required rate of return on this investment, given its future cash flows and its risk and all that. Sometimes we'll refer to interest rates as discount rates, and discounting is when we take a future value and try and get its equivalent value in today's dollars. We discount that future value back to the present. Now, the opposite of that is if we take a present value and we compound interest out into the future to get its future value. Now, we can also view interest rates as opportunity cost, and that's what I was touching on earlier. The opportunity cost of $100 now is $110 later if the interest rate is 10%. So typically you can have more consumption later or less consumption now. And so that's the opportunity cost of your money, what you could have earned had you not spent it or invested it in some other way. So let's take a closer look at this build-up approach now. We've got start out with our building block. Our bottom one, although it's on the top in the slide, is the real risk-free rate. Now, the real rate is after inflation's been subtracted. So just as an approximation, if the interest rate's 5%, you have 5% more dollars or euros or yen at the end of the year, and the price level's gone up 3%, your purchasing power, the amount of stuff you can buy at the end of the year versus the beginning of the year, is 2% more. The 5% rate minus the 3% inflation. So about 2% increase in purchasing power. So the real risk-free rate is, without taking any risk, or at least not any default risk, might still have inflation risk. But the real risk-free rate is how much more stuff you can have in the future. Now, when we add the expected inflation to that, we get the nominal risk-free rate. Nominal rather than real. Nominal tells us how many more currency units we get, how many more yen, how many more euros. The real rate tells us how much more stuff we can get. And the difference is the inflation rate. Now, we've got the nominal risk-free rate, and typically we'll use that for treasury securities of governments that don't default on their debt hardly at all ever. And that's our risk-free rate. Now, for corporate securities, bank loans, things like this, we're going to add a premium to that for risk, the risk premium. And the components of that are going to be a premium for default risk. The probability that the loan, the payments just won't be made or won't be made on time. We also expect a little higher interest rate, a higher required rate of return on investments that are less liquid. That means how easily can I convert this investment back into spendable cash? And then the third one we've got listed here is a maturity risk premium. The longer the maturity on the security you're investing in, the higher the maturity risk premium. Higher yields for locking yourself into a longer holding period. So that's, and we'll see this in various guises, but that's our basic build-up method. From the real risk-free rate to the nominal risk-free rate to the nominal bond rate, which includes these three risk premia. So now if I can find the next button here, we'll jump right in and start doing some numbers and definitions. We're going to start here from the stated annual rate. And we'll state most all our interest rates as annual rates unless we say they're different. So with semi-annual compounding, that means that we would earn 6% every 6 months, twice a year. So our effective annual rate of return is going to be higher when our compounding periods are shorter than annual. Now, if it's just annual compounding, we're going to put in $100 at the beginning of the year, get $112 at the end. But if we say, well, the stated annual rate is 12%, and the compounding frequency is twice a year, semi-annual compounding, then we take half of that 12%, and we compound that and see that $100 invested at the beginning of the year would turn into $112.36, so slightly more. And the next thing I want you to see from this slide is that the more frequent the compounding, the higher the effective annual rate or effective annual yield. So with quarterly compounding, your effective annual rate's 12.55%, and with monthly compounding, it's a little higher than that, 12.68%. Now, this stated annual rate, it could be stated for a security. Later on, when you get to fixed income, we'll talk very specifically about some names for some rates and how they're calculated. If you look at that monthly compounding, if you had a credit card that said, well, your stated annual rate is 12%, but it's not really, because it's really 1% compounded monthly. So your effective rate on that would be 12.68%. So the more frequent the compounding period, the higher the effective rate for a given stated annual rate. So let's take a look at an example of a problem here. We've got a $100,000 bank certificate of deposit that has a stated annual rate of 3.6% and pays interest quarterly. What is the effective annual yield? Well, we've got a quarterly compounding period, so we're going to divide that stated annual rate by 4. And I'll find my button here. And we'll get a quarterly compound rate of 0.9%. So we add 1 to that, take it to the 4th power minus 1. That's our compounding. So we're earning interest on interest over these 4 quarterly periods. And instead of 3.6%, the stated rate, we're ending up with 3.649%. And that's our effective annual rate or effective annual yield to the investor on this certificate of deposit. We've got a follow-up question here. What's the effective annual yield if compounding is monthly? Well, we can divide 3.6 by 12 and get 0.4% and just do the same thing, except now we're going to raise this to the 12th power and find out we have a little higher effective annual yield of 3.66%. Next, we want to take a look at the present value of a perpetuity. Perpetuity pays forever, pays perpetually. And an example of that is a preferred stock. They're often issued with no maturity date. And this one in our example is going to pay $8 a year forever. And the rate of return is 10%. What's the present value of $8 a year forever? Well, you might think it grows and grows forever, but that's not the case. Because at each future period, the value today gets less and less and less and less. And this actually converges to a value. And that value is, for those of you who haven't thought of it yet, well, it's hard to do it that way, but we can do it this other way and say, just a minute, if I'm getting only interest each year, I must not be taking any principal out. So how much principal would I have to put in there at 10% a year in order to pull out $8 a year forever? So if you're just pulling out the interest, you can see we can rearrange that equation here. And once we rearrange that right here, we see, well, $8 divided by the 10%. If we put $80 in that account, we'd get $8 of interest at the end of every year forever. And so we say the present value of that perpetuity that pays 8% at the end of each year, when the discount rate, the interest rate we're using is 10%, is $80. Now, the future value of a single sum, well, we're just going to take that compound interest as we looked at in the effective annual return or effective annual yield, and we're going to apply that to more than $1. We're going to apply it to $200 in this case. So we're going to take $200, we're going to invest it, the interest rate is 10%, just take that as the effective annual rate, and what are we going to have 2 years from now? Well, we've shown here the calculator solution, right? And that's the calculator solution for the Business Analyst Plus, one of the permitted calculators for the CFA exam. And that's the one we recommend. Now, if you haven't yet set up your calculator, you don't know about your calculator or what the buttons do or anything, please check in the Swayzer library. There's a volume on there, actually two. One on basic calculator functions, how to set it up, how to do the various types of calculations. There's only so many types that we do in the time value of money, and they're all covered there. So if you need that, go back and have a look at that, and that'll help you through your calculator. But assuming you've done that, well, we put n equals 2. 2 periods from now, the interest rate's 10%, enter that as a whole number. We've got our present value, today's value, 200. Our payment is 0. That means we're not going to add anything to the account at these future periods. We're just going to let it sit and gather interest. And we come up with a future value of $242. Now, it does come up as minus, and that just means, well, if you borrow $200 today, you'd have to pay back $242. If you invested $200 today at 10% a year compounded for 2 years, then you could get $242 at the end. So that's why they have different signs. The calculator is just saying, well, you've got to put it in to take it out, or if you take it out, well, then you got to put it back. So that's why we have the opposite signs on there. So don't let that derail you. Now, if we just look at the mathematics of it, we're just going to grow $200 by 10% for 2 years. At the end of the first year, clearly we've got $220 there, and so first year, we make $20 of interest, 10% of 200. Now we've got 220 there, and now we earn 10% on that. We earn $22, so altogether we earn $42 in compound interest, and here's how we grow a present value into a future value. 1 plus the periodic interest rate to the power, which is the number of periods over which that interest rate compounds. Now, we can just go the other way. Instead of multiplying by 1 plus the interest rate to grow it into a future value, we divide by 1 plus the interest rate. We call that discounting, and we can get the equivalent present value. So there's a couple of ways to look at this question, and I think it's important that you understand these. We could say, well, how much would you have to put in the bank today at 10% a year in order to have $200 2 years from now? So that's one of the questions that we're answering here. We could also say, well, if you're prepared to pay $200 back in 2 years, how much could you borrow today? So we're getting these equivalent amounts between time $2 and time $0, present value dollars, based on an interest rate of 10%. So here's the calculator solution. Here we've computed present value instead of future value. Now remember, with your time value of money keys, there's 5 keys. You put in 4 values, ask it the other one. If it says error message number 5, then perhaps you've got the future value and the present value both in with the same sign. That's what that usually indicates. Fix one of them, should be good to go. Mathematically, we're just dividing. We're dividing by 1 plus the interest rate twice. So we've got the exponent 2 there, 1 plus 1.1 squared. So the present value, 165.29. That's how much I'd have to put in the bank today if I were going to get an effective annual return of 10% with annual compounding. That would turn into $200 in 2 years. So that's some of our basic moves here. Now we're going to talk about an annuity instead of a single payment. We're going to talk about a series of equal payments, and that's what an annuity is. An ordinary annuity is defined as one that starts 1 period from now. And that's pretty normal. If you go get a loan, it's a monthly payoff loan like a car loan. Hey, you borrow the money this day, your first payment's 30 days later, or approximately 30 days later. This is an ordinary annuity. So we're going to take a present value of an ordinary annuity, and mathematically, if we have this interest rate, 10%, we can divide the first payment by 1.1, the second payment by 1.1 squared, third payment by 1.1 cubed, take the present value of each of those 3 payments and add them all up. So I guess we could say that this present value calculation, it's just additive. If you have a number of payments in the future, then you just take the present value of each of them and add them all up to get the present value. Now, with your calculator, the difference between what we did before is now we put in a payment of minus 200, and we set the future value to 0. Excuse me. And then calculate the present value. And this answers the question, how much would I have to put in the bank today to take out $200 1 year from now, $200 2 years from now, $200 3 years from now, and just exhaust the account? And so that's the calculator solution. We've got 3 payments. And notice I've got that red arrow there, the big red arrow, not those little red arrows, this big red arrow right here. That reminds you that when your calculator is in end mode and you do present value of an annuity, you are going to get the time 0 value. Or more generally, you're going to get the value 1 period before that first payment is made. We may see that later, or you may see it in some other problems. What if we had a stock and we say, well, it doesn't pay any dividends for 3 years, then in the 4th year it starts to pay dividends? Well, I'd use, and they're going to be level in the future after that for however many years. Well, if I calculate the present value of that, and those payments begin 4 years from now, the value I'm calculating in end mode is 3 years from now. That's why the big red arrow. When you do the present value of an ordinary annuity, or I could say with your calculator, when you're doing the present value of an annuity in end mode, the calculator is going to tell you the value 1 period before that first payment. So that's an important thing to remember when you're setting up and dealing with these problems. Now, the future value of an ordinary annuity answers the question, well, if I put a deposit into an account that returns 10% compounded annually, and I do that for 3 years, how much will I have 3 years from now when I put that last deposit in there, that last $200? So the future value, and look at the red arrow again, the future value of an ordinary annuity, the future value of an annuity in end mode on your calculator gives you the value on the date that last deposit is made, or taken out, I guess we could figure, in some cases. But for our purposes here, the future value is usually about making investments into an account, like a retirement account. If I put in this much a year, each year for the next 20 years, how much will I have at the end? Given some assumed interest rate, some annual compound rate of return. So look at what's going on in calculating this future value. That first $200 payment is going to earn interest at 10% for 2 years. That second $200 is going to earn 10% interest between time 2 and time 3. Oop, make an arrow there. I think I can. There we go. And that last $200 doesn't earn any interest, so we just add that. And we see our future value here is $662. If we want to do this on the calculator, we put in the payment minus 200, the present value as 0, nothing in the account to start with, and calculate the future value and get the same answer, thank goodness, 662. Now, you may have occasion to do a problem where the first payment is not in the future but today. This is how it is if you win most lotteries and take a series of payments. They aren't mean enough to have you come in and say, well, yes, you've won $4 million, and come back a year from now and we'll give you your first payment. That would be pretty cold. So they give you the first payment when you show up, when you turn in your lottery ticket. So that's like an annuity due. If you won $1 million lottery that paid you $50,000 a year each year for the next 20 years starting today, well, remember that last payment would come at 19, would come 19 years from today, which is the beginning of that 20th year. So for an annuity due, see where the red arrow is now? It's on the date of the first payment. So unlike when we were in end mode, now we can put that in beginning mode. Now, you see we've got $200 that earns interest for 1 year and $200 for 2 years. But now we're taking the present value, so we're dividing by each of those terms and adding them up. So the $200 comes today, $200 a year from now has that present value, $200 2 years from now has that present value. So the present value of those 3 payments, $547.11. If we want to do this on our calculator, we put it in begin mode. When we put it in begin mode, present value gives us the value on the date the first payment is made. So once we put it in begin mode, we can put, well, there's 3 payments. They're $200 a piece. Our interest rate, our discount rate here is 10%. The future value is 0. Calculate the present value and get $547.11. So this kind of rounds out this annuity part because now we've got the future value of an annuity due. Now, when we were in end mode on the calculator, the arrow was here, the date the last payment went in. For an annuity due, an annuity that starts right now, if we calculate the future value, and this is just how your calculator works. When you need to do this calculation, then you want to put it in begin mode in order to get that future value. So let me clear this off the slide and see what we're looking at. Okay, so now this $200 earns interest for 1, 2, 3 years at 10%. This $200 earns interest for 2 years at 10%, and this last $200 earns 10% interest by time 3. So we're calculating a time 3 value, and as I mentioned, with your calculator, we put it in begin mode. 3 payments, 10%, each one's $200, present value 0, future value 728.20. Same as we got with the mathematics, which is a good thing. That's what the calculator is supposed to do. Now, if we want the future value of uneven cash flows, hopefully you've picked up from what I've said so far that we can just compound the interest for each of these and add them all up. So we say, well, okay, now the account, we're going to deposit $300 a year from now. We're going to deposit $600 2 years from now. We're going to deposit $200 3 years from now, how much is in on this date? Now, using these timelines, and that's what I've drawn out here, when you're first doing these problems, or even after a while, and even on the exam, if you run into any kind of a problem that's not dead obvious to you what's going on, draw this timeline out. Okay? Put the amounts going in as positive numbers. Put the amounts coming out as negative numbers, and then look and see what you've been asked for. In this case, we're representing a problem that says, well, how much would you have at time 3 if you put in $300 at time 1, $600 at time 2, $200 at time 3, and the interest rate, the effective interest rate is 10% a year. So let me clean some marks off there so you can see this. Well, that $300 earns interest for 2 years. The $600 earned interest for 1 year at 10%. The $200 comes in at time 3. And so there's our total that would be in the account at time 3. And if we put our all these like this, we've got the calculator solutions, right? We've got no payments in here. Payment is 0 for all these calculations. So 2 periods, 10%, present value is 300. How much is the future value? Well, that's this number right here. So we add all those up, and there's our future value with uneven cash flows. Now, in other parts of the curriculum, we'll talk about using the cash flow keys on the calculator, and in that case you can do problems like this by putting in the individual cash flows, the interest rate, and then seeing what the value is. Let's go back the other way. Simple enough. Now, instead of compounding to get future values, we're going to get present values by discounting that payment at time 3 back 3 periods, the payment made at time 2 back 2 periods, and that first payment back 1 period. Add up those 3 present values and get 918.86, or we could get calculator amounts too and find out that the present value of those 3 uneven cash flows is $918.86. And I mentioned using those cash flow functions. So let's do a couple of problems and see how we might see these in practice. What's a monthly payment on a $100,000 30-year home loan with a stated rate of 6%? Now, I didn't write it in the problem here, but mortgages usually pay monthly. The great majority of mortgages pay monthly. And so we've got a stated annual rate of 6%, but we've got monthly payments we've got to figure out. So the first thing we have to figure out, well, how many monthly payments are there in 30 years? Well, there's 360 of them, so there's our n value. Now we can take 6 and divide it by 12, so for I over y on your BA 2+ calculator, you would put in 0.5 as the monthly interest rate. So we've got 360 monthly payments. We've got a monthly interest rate of 0.5%. The present value is $100,000. The future value is 0. We're going to pay it all off by the time we make the last payment. This is what we call an amortizing loan. All the payments are equal. They're like an annuity. And then that last one just pays off the remaining piece of the loan and the last bit of interest for the last month. And so that payment comes out to $599.55. So we've figured out a home loan on a 30-year loan with a 6% stated annual rate per $100,000 borrowed. Now, the second question, our follow-up question here, is how much of the remaining principal, the payoff amount on the loan it's referred to sometimes, how much is the remaining principal just after the 85th payment is made? Well, you buy a house, you own it for 85 payments. What's that, about 7 years? A little more than 7 years. I guess that's maybe average, maybe a little longer than average. But at the end of 7 years, you sell your house and you, well, I got to pay off this loan. Well, how much do you have to pay off? Well, for most loans, there's no prepayment penalty or anything. You just pay off the present value of the remaining payments, discounted at the rate stated in the loan. So the calculator already knows I over Y. it already knows the future value. And when you did compute the payment, now it knows the payment. So you can change these one at a time or just change two of them and then recalculate the other one. In this case, N is changed. We've just made the 85th payment. There's 275 payments left. We're in end mode on our calculator. And so all we have to do is put in the remaining payments and calculate the new present value. The new present value is the present value of those remaining payments discounted at this stated annual rate of 6% or 0.5% per month. So that's the payoff. That's the remaining principal outstanding on your loan. So after 7 years, how much principal have we paid down on this loan? We've paid down, what, just over $10,500 in 7 years. So that reminds us of something. Early on in a loan, much of an amortizing payment is the interest. And toward the latter payments of the loan, most of the payment is paying off the principal amount, because a smaller and smaller piece of that payment is interest as we move through the loan period. Let's take a look and apply these concepts again in another way to a retirement savings problem. Client has $75,000 in savings today. Comes into your office, says, I'm going to retire in 20 years. When I retire, I need 25 payments of $62,000 a year. And that first payment I'm going to need 20 years from now. The account's expected to earn 7% per year. Now, luckily, this client knows, I guess, exactly when he or she is going to die. So they need 25 years worth of payments. So we can figure out this problem. How much is needed on the day of retirement to fund that retirement? Well, it might help, I think, at this stage to take a look at a timeline and say, well, we're talking t equals 20. I guess I'll extend that over this way. T equals 20 years from today, and we're going to have our first payment of $62,000 come out right then. And then every year for 25 years, and when would the last one be? I'll put some dots here, I guess. When would the last one be? Well, if they're going to be 25 payments, that last one would come at, 44. T equals 44. So now let's look at how we'd solve this on our calculators. We'd put it in begin mode, right? Because that first payment is going to come out at time 20. And we're calculating a time 20 value. So we know there's 25 payments, there's $62,000. The future value is 0. The account's going to be exhausted when that 25th payment is made. The interest rate is 7%, and we're all done except for calculate the present value. So what we've shown here is that we need $773,099 in the account in order to take out $62,000 a year that day and once a year for another 24 years when the interest rate is 7%. In this case, 7% is what that money in the account is earning each year. So let's look at our follow-up question. Now, what annual deposit must she make at the end of each year for 20 years to reach her goal? Well, now we know we've got, let me draw a timeline again for you. We've got a time 20, oops, I better slow down for the machine here. We've got a time, I don't like that at all. Let's do it right. I'll put T equals 20. I must write slowly with this. Okay, so at time 20, we need this much. So now that's going to be our future value. And when do these payments come? They come at the end of each year, and we know the client has $75,000 in savings now. So let's put 75K in savings, and the question becomes, how much do we have to deposit each year, starting a year from now at time 1, in order to have this $773,099 at time 20. So now we're going to be in end mode. our first deposit is coming one period from today, and the only other trick we've got going on here is we do have a present value for this of $75,000. So we put it in AND mode. We know the future value, put that as a negative. We've got our present value, that's how much is in the account today. There's going to be 20 payments, and we're going to get the payment we must make in order to have that $773.99 at the day of retirement. And so the payment is going to be $11,778.68. That's the deposit must make every year for 20 years. Now notice that's the same as the present value. And that's right, because that's what's going into the account. Had we gotten a negative payment amount here, it would mean that we've got so much in it today, we could take it out a little every year and still have $773.99. You might want to try that on your own calculator and put in a much higher present value and see what it means to be for that payment to be negative, because you need to know how to interpret that. Okay, let's look at another problem here and apply these concepts. Elmer's won his $4 million state lottery. He's been offered 20 annual payments of $200,000 each beginning today, or a single payment of $2,267,000. What's the annual discount rate used to calculate the lump sum payout amount? So some lotteries give you the choice when you win. That's nice. You can take these 20 annual payments of $200,000 each beginning today, that's an annuity due, or a single payment, a lump sum. So now we want to know, well, what discount rate are they using to claim the present value of this annuity is $2,267,000? So here's the way we'd set that up. We'd put it in begin mode because that first payment is today. So we're trying to calculate the interest rate that will make the present value of 20 payments of $200,000 each equivalent. And if we compute that, it turns out to be 7%. So, remember, 5 things on these time value of money keys. We've calculated present value, we've calculated future value, we've calculated the payment amounts on a home loan, we've calculated the discount rate that these lottery officials are using to translate your payment stream you won into a time zero payoff, a present value of those. And so our last trick, we could solve for N, the other one of those. So Elmer borrows $100,000 at 9% and will make annual end-of-year payments of $13,966. How many payments must he make to pay off the loan? Well, it's a little bit of a contrived problem, there's no doubt about that, but we're going to solve for N. So, what is the future value? Future value is 0. Present value is $100,000. He's going to borrow that. He's going to make these payments, so they have to have the opposite sign of the present value. The interest rate we're going to use is 7%, so we remember we put that in as 7 as a whole number. And then we just compute N equals 15. So if he makes 15 payments, he will just have paid off that loan if the interest rate is 7%. Well, I hope that's a good introduction for you and you get comfortable with these. Don't forget, draw timelines. When you're doing present or future value of an annuity, think about whether you want to be in end mode, where you're getting the value when the last payment goes into the account, or the value one period before the first payment is made, or whether you want to be in begin mode, so your present value is for the day the first payment is made, and your future value is for one period after the last payment is made or after the last deposit is made. So those are the important things to take away from this, and then keep these principles in mind as we look at bond valuation and stock valuation and all sorts of other valuations where we're going to use these techniques throughout the Level 1 curriculum.